actually starts recording. Right. Hey there. For those listening, well, for all of you, but especially those listening, I'm David, and I'm the coordinator of the Maths Learning Centre. This is a Maths 1A revision seminar in semester 1, 2017. Hello from the past. I'm sort of doing a request session this semester, and we'll see what it turns into. So, the first question that I've been asked that I've never actually talked about before is the Cayley Hamilton Theorem, which is awesome because it's one of my favourite theorems. So I'm going to talk about that, and then we'll move on from there. This is taking from a request I've been sent earlier. All right. So the Cayley Hamilton Theorem, I believe, is the last theorem in Maths 1A. And it's a most awesome theorem. But it might take me a little while to get there to really make you feel how absolutely awesome it is. So, all right. It goes like this. So, if you've got a square matrix, square meaning it's n by n, some n. I'm not quite up to the Cayley Hamilton Theorem yet. It's going to take me a little while and I'll get there eventually. If you've got a square matrix, then matrices have all these things that you can do to them. You can multiply them by each other, and you can add them together, and you can multiply them by scalars. And you can square them if they're a square matrix and cube them. So a squared is a times a, and a cubed is a times a. And you can calculate all the normal things that you can normally do with numbers on matrices. So you can, 5a and a plus an a squared and an a plus a squared plus 2a, and any number of things you can calculate from a square matrix A, just like you can with a number, okay? And if you have a polynomial, e.g. like g of x, maybe x cubed minus 3x plus 5 or something, then you can calculate what that polynomial works out to for various numbers, and you can factorize it, and all those sorts of things. And calculate g of a number. And, well, if I can calculate, powers and multiplication and addition on numbers when I do a polynomial, it's not at all unreasonable to expect I should be able to do it on matrices too. And so what I'm going to do is I'm going to think about taking a polynomial and subbing a matrix into it instead. So maybe I'll go I want to do something like g and sub a matrix into the polynomial instead. And that's fine because, I can just make sure I'm very careful about what I mean by that. So if g of x was like x cubed minus 3x plus 5, I could totally calculate g of a, and that'd be a cubed minus 3 of a plus... I can't just go adding 5 to a matrix because my matrix might be 3 by 3 and have 9 different numbers in it, and you can't just add plain numbers to matrices. So I'm going to have to interpret this 5 as like 5x to the 0, and so I need to put a matrix in that spot, so I'm going to put the identity. And that's how I'm going to calculate a polynomial enacted upon a matrix. And this will be some new matrix. I don't know what it's called, but there will be some sort of matrix with numbers in it, right? That will be this answer. And then I can ask myself, well, now that I've got a matrix with a polynomial with a matrix in it, can I do all the things that I used to do to polynomials, like factorize them and find what g of something is and figure out its zeros, so which matrices will make it come out to 0? That would be a cool thing to figure out. Okay? And what I'm going to... Well, that's really hard, actually. But what I am going to do is I am going to see what it does to the information that I know about a matrix. What does calculating the polynomial in a matrix do to the things you know about the matrix? And the things that are the coolest thing to know about any matrix are its eigenvalues, because eigenvalues are like the best thing ever. And so, what if I did this? If I had a matrix A with eigenvalues, I don't know, 1 and -1 and 7 or something, and I had a polynomial g of x, it's like 2x squared minus three something, then I could try and figure out what the polynomial did to the eigenvalues of the matrix. So I could find g of a, which would be like a 2a squared minus 3i, and it would come out to whatever it came out to. Maybe I should put a matrix in there. Can I be bothered calculating its square? No, I can't, so I'm not going to do that. So I could put a matrix in this spot here with eigenvalues those, and I could do a polynomial. Yeah, I'm going to do it. Let's see if I can figure out a matrix with those eigenvalues. I suppose I could do this always, couldn't I? Like that. That's got those eigenvalues. Alright, and g of a would be this. That's 3 times I, like that, which would come out to whatever it comes out to. 1, 5, minus 5. Oh, interesting. 6 plus 10 plus 42. Oh my goodness. 6 plus 10 would be 6. Just a second. 42 plus 10 would be 52. Plus 6 would be 58. 0, 0, 0. Nice. 0, 1, 0, minus 2 plus 14 is 12. 0, 0, 0. 0, 0, 0. 0, 0. Wasn't too bad, actually, I have to say. So I reckon I do all this in one go. 2 times 1 minus 3 would be minus 1. And 2 times 58 would be 116. 49. 2 times 49 would be 98. Right.
It should be 24.
Totally should be 24, thank you. I'm glad to see that someone other than me is paying attention, because I certainly wasn't. So, okay, so I get this matrix. It's a great matrix. Lovely. And I know what the eigenvalues of this matrix are, because it happens to be a triangular matrix. Its eigenvalues are minus 1 and minus 1 and 95. Watch this. If I do G on the 3 eigenvalues of my original matrix, I get 2 times 1 squared minus 3, which is minus 1. And 2 times minus 1 squared minus 3, which is 2 times 1, which is also minus 1. And 2 times 7 squared minus 3, 2 times 40, 95. Oh, look at that! It's the eigenvalues of the new matrix! It's the coolest thing! And it's got one of the best proofs of all time. Yay! Okay, so they're the eigenvalues of GA. This is the coolest theorem. You don't have it in your lecture notes, and it totally should, because it's the best thing. Okay? And it doesn't have to be that complicated, right? It could just be that if I had A has eigenvalues 0 and minus 2 and 2, then a squared will have eigenvalues 0 and 4 and 4, because I'll just square the other eigenvalues. It's beautiful stuff. And even better, you know how these two, I've listed 4 there twice? It really will be there twice. Okay, if 2 of them produce the answer 4, it will have multiplicity 2. It's super cool. All right. So that's not the Cayley Hamilton theorem. It's like, I don't even think it has a name. It's just the coolest theorem ever. Well, the second coolest theorem ever. The Cayley Hamilton theorem is the coolest one. So, here's the really interesting thing that we can do with this. If you have a matrix, right, just some random numbers, then I can make a polynomial from my matrix. It's the characteristic polynomial. Every matrix has a polynomial. And it'll have a polynomial. This one will be lambda minus 2, lambda plus 3, lambda minus 7, because that's how you make a characteristic polynomial if you already know the eigenvalues. Alright, and this would expand out to be something. Can I be bothered? Sure I can. Lambda squared plus 3 lambda minus 2 lambda would be plus 1 lambda minus 6. Lambda cubed minus 7 lambda squared plus lambda squared minus 7 lambda minus 6 lambda plus 40. Okay, so that's what it becomes. I don't technically need to do that, but it's just making me feel better. Okay? And that's a perfectly good polynomial. I've used lambda instead of x, but it doesn't really matter what the variable is. So since it is a polynomial, I should be able to sub the matrix A into it, and I'll get a new matrix, and I know what the eigenvalues of that new matrix will be. They'll be what I get when I put the zeros, when I put the eigenvalues of A into that polynomial. So I can make P of A, which would be A cubed minus 6A squared, damn it. A squared minus 13A plus 42 of the identity, because that's what you do when you sub in matrices into polynomials. And that matrix, whatever it works out to be, will have eigenvalues P of 2 and P of minus 3 and P of 7. Alright? But when I sub 2 into this polynomial, it's really this, and so I'm going to get 0. Because 2 minus 2 is 0 times all the rest. And when I sub minus 3 into this polynomial, I'm going to get 0. And when I sub 7 into this polynomial, I'm going to get 0. So what I'm going to do is I'm going to make a matrix. I mean, this is a single matrix, so I'm going to figure out what it is eventually. You know, some sort of matrix there. This matrix, its eigenvalues are all 0. Which is really kind of very interesting. That's cool. Now, it is possible for a matrix to have all of its eigenvalues being 0, but not be the 0 matrix. Okay, it could just have zeros all down the diagonal and then other stuff up in the corner, and it would still have all its eigenvalues 0. What the Cayley Hamilton theorem says is it's not just that all the eigenvalues are 0, the whole matrix is 0. The 0 matrix. So not just that the eigenvalues are 0, but the entire matrix is 0. If you sub a matrix into its own characteristic polynomial, you'll always get the 0 matrix as the answer. And that's kind of cute, right? You go, oh, well, we're going to sub matrices into polynomials. Well, here's a polynomial. Let's see what happens here. And the answer always comes out to 0. And why would you care? Well, my goodness. Do you not have a soul? It's so cool! Right? for those of you who had both me yelling and then laughing through the headphones, someone said, I feel sorry for the guys listening on headphones for this. Ah, well, more for you, you didn't come in person. But it's kind of useful in other ways. Well, I don't know if it's useful, but interesting. What this means is that with any matrix, I can construct its bigger powers from its smaller powers. So what it means is that I could say, well, for this matrix, since a cubed minus 6a squared minus 13a plus 42i is 0, I can say that a cubed is the same as 6a squared plus 13a minus 42i. And what I've managed to do is rewrite the third power of a in terms of the smaller powers of a. And actually what it means is that every power of a can be written as a combination of these smaller powers of a. I could times everything by a and get a to the 4 is 6a cubed plus 13a squared minus 42a. But I already know what a cubed is, and I can sub that in there. A minus 42i a squared. And if I expand that all out, I'll get something. 36a squared what do we got? 60 plus 18. 240, 252. So I've got, what, 49a squared plus 36a minus 252i. So I've managed to make a to the 4 out of a squared and a and I as well. It's a classic Maple TA question in Maths 1a to do this. And not just, and so I should be able to make a 5 out of those 3, and a 6 out of those 3, and a 7 out of those 3. The numbers usually get bigger and bigger and bigger as you go, but that seems reasonable. And you can imagine that the bigger the power is, the more efficient it would be to do this than to actually multiply the matrix 50 times or whatever, if you wanted a to the power of 50. But also from an algebra point of view, I can now say, let's just blow your mind, is that all of the powers of a are spanned by a squared and I like vectors are. I can use a squared and I as a basis for a subspace of matrices. Love subspaces too, they're my favourite. They're all my favourite really. It's like that wonderful children's book with the little baby bears. Right. Not just that we can do the inverses using the same rule. If we go back to here, we go back to the original. Where was the original? Here it is. A cubed minus 6a squared minus 13a plus 42i equals the 0 matrix. I can rearrange this. I can remove all of these things from over here and then end up on the other side. Right? And then I could take an A out of all of this. Now, A is A times the identity, right? So if I remove an A from it, I'm going to be left with an I. And look, we're nearly there. If I divide the right thing by 42, because 6 divided by 42 is a 7. We have A times a matrix equals the identity, therefore this matrix must be the inverse. Look at that. We can write the inverse of A as a linear combination of A squared and A and I as well. So just so you know that there's this classic Maple TA, an exam question which says, this matrix has these eigenvalues, find A inverse as a linear combination of the powers of A. Technically, this is the safest way to do it, because at no point did I assume the inverse existed until I found it. Some people, what they do is they multiply everything by A inverse and then rearrange the equation, and that's an acceptable way of doing it if you can be sure the inverse exists in advance. So if you want to do it that way, you have to tell the person reading it how you know the inverse exists. But this one, I know the inverse exists because I can multiply A by something and get it equal to I. So there you go. So every power of A is made like this. What happens with some matrices is because you're always doing the same combinations of A squared and A and I, you can come back to where you started. If you do a high enough power of A, you can get back to A again, if you've got the right sorts of eigenvalues, which is kind of cool, really. So matrix multiplication, matrix powers, sort of turns into something that's a little bit circular. It sort of comes back to things you've seen before, which is a little bit like the way complex numbers work, actually. Their powers of complex numbers are a bit circular. They go round and round and round. And in fact, you can build the complex numbers out of matrices if you want, which is also cool. So there you go. That's the Cayley Hamilton Theorem. Pretty much that's everything that you might want to know about it, plus some other stuff that you didn't want to know, but I think is really cool, so I told you anyway. There you go. So I'm going to not talk about that anymore, unless you have any questions about it. Which I'm completely happy to take. Yes?
Do you need to assume the inverse exists to take it to the side or not?
What's that?
When you do the last step,
yep.
Is that proving that the inverse exists?
This proves the inverse exists. Because the definition of inverse existing is that there is a matrix you can times by A to get the identity.
Yep.
So if you're able to multiply A by something to get the identity, then that something must be the inverse by the definition of inverse. So I suppose you could say that, by definition of inverse, if you really wanted. Cool. All right. So that's using the Cayley Hamilton Theorem and the other theorem, which is an awesome theorem. Okay, there are so many other awesome things about eigenvalues. There's this really cool thing about two matrices. If you can multiply them both ways, you multiply them one way, you'll get a matrix. Multiply them the other way, you get a matrix. And if you can reverse the order of multiplication, they have the same eigenvalues, except the bigger matrix has zeros as the extra ones. It's so fabulous, for no good reason other than everything's connected to everything else, which to a mathematician is the best thing ever. So, yeah. All right, I'm going to take a request from you guys who have come today rather than from my previous emails. It could be the same thing, of what you would like me to talk about next. So what do you want me to talk about next? Yep?
Markov chains.
Markov chains. Okay. Let's look at that. Can I borrow someone's lecture notes? Oh, this is closer. Thank you all the same. I will probably forget to give them back to you, so please remind me. Did you have any specific questions that you wanted to know about Markov chains? Does anyone have any specific questions they'd like to know about Markov chains? Things that sort of they came across and went, what's going on there? All right. So, I'm looking at your notes just to make sure I match up, because more than one course does Markov chains, and being in the Maths Learning Centre, I sometimes have trouble remembering which bit is in what course, so I just want to make sure it matches with what's in your course. Okay. All right. I'm going to add to your thing dynamical systems. Alright, so if you are studying for an exam, or studying ever, and you have a particular topic in a particular course, a good question to ask yourself is, why have they put that topic here in this course? So we're going to ask that question ourselves. So, it appears that all of this is under the heading of applications of eigenvalues and eigenvectors. So the reason they put Markov chains and dynamical systems in your course is because you use eigenvalues and eigenvectors to solve those problems. So that's why it's there. That's a good thing to know, because that means that if you are faced with things about dynamical systems or or Markov chains, then you can expect to need to know about eigenvalues, because that's where it is in the course. It's a fairly basic question for this one. Now, the other bigger why of why is it in this course is probably to do with the fact that various types of science and engineering applications will use Markov chains later on. Not all of you. You know, this course for Maths 1A is designed to service a whole lot of different people, and different bits of it will be useful for different people. But Markov chains will come back in various sciences and engineerings, and so they put it in here in the hope that it'll be useful, because by the time you do it, it'll be way more complicated than this, and hopefully you'll get some more courses about them along the way. So the idea is that you're going to have some sort of situation which is described by various numbers. By some numbers, x1, x2. Alright? And when you describe situations by numbers, you chuck them in a vector like that. Okay? And that's what you did when you did optimization as well. You had some situation which was described by some numbers, and usually those numbers were the amounts of various things. And so that's what we're going to do in our dynamical systems and Markov chains, and maybe these numbers are going to be populations of different age groups of spotted owls, classic example, or maybe they're going to be the percentage of people who live in a certain area in a country, or maybe they're going to be the probabilities of certain events happening, or who knows, they could be any number of things. Forces in a system, all sorts of things they could be. Right? And this is all going to go together to be a vector. Of course, when mathematicians talk about vectors and there's going to be matrices involved, they write their vectors as columns. Right. And when you put an X with an underline or in bold, underline in handwriting and bold in the notes, it'll be a column vector. Okay, and what the idea is, you've got a situation described by these various numbers, and you'll look at it at various time points. Okay, one step after another. And so you'll go here at time t, usually time t equals 0, you're going to have a vector describing all the numbers I'm interested in at time 0. I don't know what it's going to be, who knows. And here at time 1, we're going to have a vector which describes all the information, that's going to have a 1 in it. A vector that describes all the information at time number 1. And here at time 2, we're going to have a vector that describes all the information at time 2, and so on. Okay, there'll just be this big list of times and the matching vectors. Now you're used to functions that do that, it's just that you're used to having one number, right? You have t equals 0 and you have 1 for a number, and then 2 for the next number, and then 4 for the next number, and then 8 for the next number. You're used to functions of single things. What we have here is a time which produces a vector as its answer. Sweet. The thing that makes Markov chains and dynamical systems special is that the way to get from here to here is to multiply by a matrix. I write it as A times because you put the matrix on the left-hand side. So the concept is that x1 is the matrix times x0, and x2 is the matrix times x1, and x3 is the matrix times x2. So to figure out what the next one is, you multiply by this matrix. And certain situations will correspond to things where matrices can describe the way that the system changes. And so the big version that they have is that they say that xn plus 1 is a times xn. That's how you'd normally see it written in your notes. Though they use a k, apparently, in the notes. Okay. Sweet. So something in the way that the system is described will tell you that there is a matrix. And the fact that it's a matrix means that each of the coordinates can be calculated from a combination of the coordinates of the other one. But usually they'll just tell you the matrix. So the example in the notes has a system where it says that the number of owls at time n plus 1 is 0.5 times the number of owls at the previous time point plus 0.4 times the number of rats at the previous time point, and the number of rats at the previous time point is minus 0. Sure, and why shouldn't it be? Okay, so that's what the one in the notes looks like. You have this description of these numbers which describe the situation. These are my numbers, the number of owls and the number of rats. That's the numbers that describe the situation. And we're going to be able to calculate those numbers from the numbers previously, like this. And what we want to do is we want to rewrite this as a matrix. Okay? So I can imagine this as being produced by doing a row times a column. Damn it. That's the idea behind this. We want to rewrite this as the vector which contains all my numbers is a matrix times the vector which contains the previous numbers. And if I think of this as a row times a column, it'll be 0.5. Ta-da, okay? And that's my matrix A that I'm interested in. So any system that you can imagine like this, you can imagine like this, and you can use the theory of dynamical systems upon it. All right? Sweet. And you can even do this with probabilities. Anything where there's a list of numbers which describes the situation at a particular time, and that list of numbers can be calculated from the previous list, usually can be done with the dynamical system / Markov chain sort of situation. Right. So, there is one question you want to know about any of these systems, and it is this. What's going to happen if you let it run and see what happens in the time, in a while? So if I let this system run, and I pick some numbers to start with, and go, pick some numbers to start with, times by the matrix, and we get an answer, times by the matrix again, and we get an answer, times by the matrix again, and we get an answer, times by the matrix again, and we get an answer. If we just keep doing that over and over and over and over and over, where are we going to end up? That's what we want to know. So we start with x0, we go to x1, we go to x2, we go to x3, and we go... Not that there is such a thing as x infinity, but that's where we want to see. What happens if we do it forever? Where will it go? Or at least long enough so that it stops changing. Okay. And Markov chains and dynamical systems and the special dynamical systems that are Markov chains have two different approaches to this. Okay. I'd need to do an example for this. So the general idea is that I know that getting from here to here is the same as timesing by A, getting from here to here is the same as timesing by A again, getting from here to here is the same as timesing by A again. I'm going to continue to do that multiple times, and so what we're going to end up with is that xn is going to be A like that. You just keep multiplying by A over and over and over again, which is the same as doing a power of A. And one of the things that eigenvectors can do is they can diagonalize a matrix. So I can find a P so that P inverse AP is a diagonal matrix. Which means that if I multiply by P here and multiply by P inverse here, I'll get this. And then if I do A to any power, it'll be multiplying this by itself all these times, right? So A to the N will be like P, D, P inverse, P, D, P inverse. Trying to find my eraser, there it is. P, D, P inverse. And look, all these P inverses will cancel each other out. And so we just end up with P, D to the N, P. Which is sweet. Because when you do a diagonal matrix to the power of n, that's totally just the same as doing all the diagonal entries to the power of n. So it's awesome. So that means that I can just figure out what happens when the d goes to the d when the power goes to infinity. So I'm just going to do not that example, but just have an idea of what might happen. For example, suppose A had eigenvalues 1.2 and 0.8. Sure, that'll do. Then what I'm going to get is that A is equal to P like that. Beautiful. No, there is no 0. And so A to the N will be P like that. Because when you do a diagonal matrix to the power of n, you just do the entries to the power of n. Which means that when n goes to infinity, this bit goes to 0. Because a number that's less than 1, the bigger the power is, the closer to 0 it gets. Because imagine a half. Half times a half is a quarter, times a half again is an eighth, times a half and again is a 16th, times a half again is a 32nd, times a half again is a 64th, and so on. And so any number, even if it's just 0.99, it will still eventually go towards 0. Beautiful. Okay. Nice. Did I need to do any of that? No. No, I didn't. I'm sorry about that. As I said, sometimes I struggle to remember what's in Maths 1A and what's in the other courses. It's useful to know, right? This bit's going to disappear. But even that's not necessary. Let's think about this another way. We're going to use the same eigenvalues with eigenvectors, I don't know, 3, 2, and minus 1, 1 or something. Yes, totally independent of each other. That's important. All right, here's another way of thinking about it entirely. Watch this. Since those eigenvectors cover the entire of R2, it will be possible to rewrite whatever x0 I start with as a combination of those. I don't know what it is. since now what's the word for that? A basis. It's possible to write x naught as some combo of these. Like that. Because that's what a basis is, right? If they're linearly independent and there's two of them, they're going to be a basis for R2. That's because they're in R2. If they're linearly independent and there was two of them and I was in R3, it'd be a basis for something else entirely. But anyway. Then that means that everything can be written as a combo of those two things. And so when I multiply by A, I'm going to get that. And when I multiply by A again, even better, just a second. Wait. This is an eigenvector. I'm going to be able to multiply, A times an eigenvector is the same as just multiplying the matching number by the eigenvector. And when I multiply by A again, I'm going to times this one by A. But A times an eigenvector is the same as multiplying by the number. You don't normally have to show all this working. I'm trying to explain how it goes. And so I get A times 1.2 squared, 3, 0.8 squared minus 1. And we can imagine doing it again. If we times by A cubed, we're going to get a 1.2 cubed and a 0.8 cubed. And if we go to A4, we're going to get a 1.2 to the 4 and a 0.8 to the 4. And so we're going to get that A to the n times x naught is A 1.2 n minus 1. And then the same trick I mentioned earlier is going to happen. As n gets bigger and bigger and bigger, that number's going to get bigger, and that number's going to get smaller and smaller. So if they were both under 1, then the entire thing would go towards 0. So this approaches damn it, it's not 3 on 2, it's the vector 3, 2. Because this thing here is what xn is. So xn goes to here as n goes to infinity. Yay! So if this number was, say, 0.7, then it would have just gone to the 0 vector. And all the numbers, so the populations of the owls and the rats or the whatevers go to 0. What this tells me is that everything survives, all those numbers just keep getting bigger and bigger, but I can also know how big they are relative to each other. I know that x1, this is getting a bit confusing. So if this vector is equal to that, then I know that x1 divided by x2 is the same as 3 on 2. Because this bit will cancel out when I do the division. So x1 is 1.5 times x2. So if the x1 was, say, the number of owls, and the x2 is the number of rats, then what happens eventually is you get 1.5 times as many owls as you do rats. If they were probabilities, then you would mean that the probability of x1 is 1.5 times the probability of whatever the number 2 represents. And so you can figure out the relationship between those probabilities. Alright, so here's the thing. That's dynamical systems. And in order to do this, you would need to find the eigenvalues and the eigenvectors first. So the moral of this tale that goes there. You'll need to find the eigenvalues and the eigenvectors first if you're going to do a dynamical systems question. All right? And you don't actually need to figure out what this little a and little b are. You can do all of your working with just letting them be round numbers. You don't have to write anything as a linear combination of anything else, because it'll all disappear by the end when you do the n going to infinity. Okay. But here's the thing. Markov chains are a really special kind of dynamical system that have an extra piece of information about them, which makes this process even easier. So it's a dynamical system where the x is a list of probabilities. Or it could be proportions, doesn't really matter. So being a list of probabilities, and even better, not only is the x a list of probabilities, but every column of the matrix is a list of probabilities as well. And that's a really useful piece of information. So what that means is that all of the entries in the matrix and in any of the vectors that you might calculate are supposed to be numbers less than 1 because they're probabilities. They're supposed to be more than 0 because they're probabilities. And they're supposed to add up to 1. So that is every column adds to 1 when it's a Markov chain. Or alternatively, if all the columns add to 1, whether they're in the matrix or in a vector, then it's a Markov chain. And here is the magic of Markov chains. If all the columns add to 1, then you are guaranteed that 1, the number 1, will be an eigenvalue. And if all the columns add to 1 and every vector is made of things less than 1, you are guaranteed that not only will 1 be an eigenvalue, it will be the biggest eigenvalue. So what that means is one is the biggest eigenvalue. Now just a second, watch what would happen if 1 was the biggest eigenvalue. If that was a 1 in that spot, when n went to infinity, well 1 to the n is always 1, and we just end up with that vector. Well, it will be something times that vector, but that's what we'd end up with. So, you don't have to do any of this other stuff. All you have to do is find the eigenvalue that goes with 1. Eigenvector that goes with 1. You don't even have to find the eigenvalues because you're guaranteed that 1 is an eigenvalue. You don't have to find all the other ones. It's completely irrelevant. So if it really is a Markov chain, 1 is the biggest eigenvalue, and if v is its eigenvector, then xn goes to v as n goes to infinity. So all you need to do is find the eigenvector that goes with 1, and that's where it goes. Except, just be careful, because technically every eigenvalue has multiple different eigenvectors to go with it. You want to pick an eigenvector whose adds up to 1, because it's supposed to be a list of probabilities. So for example, now I always have trouble making up these examples off the top of my head. I always think of Markov chains as ant farms. So here is my ant farm. It has 3 little blobs where the ants can live, and little paths that go between them. Like that. And actually a little path goes from here to here as well. And this is number 1, and this is number 2, and this is number 3. And let's see, the ants that are currently in number 1, let's say that maybe 50% of them go over to number 2, and maybe 20% of them go back to number 1, which leaves 30% to go over to number 3. And maybe the ants that are in number 3, maybe, I don't know, 70% of them in number 1, 20% of them go to number 2, and 10% of them end up back in number 3. And number 2, let's say 90% of them go back to number 3, and, oh no, that's too hard. I don't feel like doing anything with more than 1 decimal place. There was a lecturer once who used to say, who used to put as one of the questions on her exam, write a problem you think you can solve and solve it. There you go, this is the problem I think I can solve. Because otherwise, see, I didn't want to put 9 because then I have to put 0.05 or something there, and that's not fun. I should say that in some of them are 0, and it's not actually possible, for example, for it to get from 2 to 1. Maybe that would have been a possibility, but, you know, too late now. Okay, so this is a description which would normally be in words in one of these questions. And so what I'm going to say is I'm going to pour 1,000,000 ants into that number 1, and I'm going to watch them walk around and see what percentage of ants are in what bucket, what corner at the end of, like, I don't know, 17 days or something, and see where they end up. So at every moment, every second, all the ants are going to choose where they're going to go randomly based on those probabilities and go to the other corner, and then they're going to do it again, and then they're going to do it again, and then they're going to do it again. And eventually, even though all the ants are moving, there's always going to be roughly the same amount of ants in every corner. It's a bit like chemistry, where you have, what do they call equilibrium in chemistry. Actually, it's exactly like that, and people use Markov chains to study chemistry processes, especially in chemical engineering. So, what you need to do is figure out how you're going to make your matrix. So I know that this is going to be the number in, that's my vector, the number in position number 1, the number in position number 2, and the number in position number 3. And they're not going to be numbers, they're going to be percentages, because they have to add up to, they have to be probabilities. Probability of picking an ant that's in that corner. Okay? And so, if this is at n plus 1, and the previous one, damn it, I'm going to call them x, y, z, sorry, because it's too hard. X, n plus 1, y, n plus 1, z, n plus 1. That's what's in position 1. Y and z, like that. Okay. Right, let's see. So, I'm supposed to make a matrix, right? So let's see. The amount that appear in X, some of them came, the amount that appear in X, some of them came from blob number 1 to begin with. Okay, so 0.2, 20% of the ones that were already here end up back where they started. Alright? So I'm going to get 20% of the ones that were in X2 are going to were in X, are going to end up back in X again. Now the ones that were in 2, 10% of those end up in X. And the ones that were in 3, 70% of those end up back in X again. So the total number that end up in X are these 3 things. 0.2 of whatever used to be in X, 0.1 of whatever used to be in 2, and 0.7 of whatever used to be in 3. Z. So to get to Y, which is number 2, I'm going to get 0.5 of whatever used to be in X, and 0.1 of whatever used to be in 2, and 0.2 of whatever used to be in Z, and then for Z, I'm going to get 0.3 of whatever used to be in x, and 0.8 of whatever used to be in y, and 0.1 of whatever used to be in z. And that's my matrix. I can check if it's all working correctly, because the columns should add up to 1, which they do. 0.2 plus 0.5 plus 0.3 is 1. 0.1 plus 0.1 plus 0.8 is 1. 0.7 plus 0.2 plus 0.1 is 1. Okay, so I've done my matrix correctly. The classic mistake is to end up with the rows adding up to 1, which means you've done it around the wrong way. The rows don't have to add to 1. For example, this row doesn't. It only adds to 0.8. All right, so that's making your matrix. And now I can figure out, I know that lambda equals 1 is an eigenvalue. And so I will do lambda I minus a. Whoa, okay. So minus a. I really should not have made this big, I'm sorry. And then lambda I would be like that. And I'm supposed to, and what's the lambda? The lambda is 1, isn't it? And what I'm supposed to, oh damn it, that's really close together, it looks like. What I'm supposed to do is I'm supposed to row reduce this to figure out what the eigenvectors are that go with this. So let's see, what have I got? I've got 0.8 minus 0.1 minus 0.7, 0.5. I'm really, really hoping that this is going to turn out the way I expect. I'm not going to put the 0, 0, 0 because there's no point writing it over and over again. I'm just going to keep doing this. So for the purposes of making this easy for myself, I'm just going to times everything by 10. Didn't really make it easy for myself, did I? Didn't even give myself even numbers to divide by them to make ones. If only I could, that'd be so awesome in an exam. It said, I choose to change the exam question to this. Okay. And we don't even have calculators anymore, do we? So I can't appeal to technology to do this. So it's likely they would have given you something a little easier with maybe some more zeros in it or something. Alright. So magic trick, and we end up with some eigenvalues, right? I can cheat because I am not in your exam. I am guaranteed that one of these rows will be the sum of the other two at least. If I go these two added together, it adds up to that last, that first column. See, minus 3 minus 5 is minus 8. Minus 8 plus 9 is plus 1. And 9 minus 2 is plus 7. So I can at least wipe out any one of those rows that I like because it must work that way. So pick one, I guess. And that's as far as I'm going right now. So bear with me for a second while I attempt to remember how to put matrices into Wolfram Alpha. Damn it. Read my own matrix correctly. It's thinking Let's go. I've got a characteristic polynomial. What am I looking for? I'm looking for the reduced echelon form. There we go. Beautiful. That's such bad form of me to give up like that. But there's a good reason they don't get you to write your own exam questions on the fly during the exam. Okay, I get this. That's a 65, I believe. Okay, you know. And so, I get to there, and then I can say that I've got a pivot here, and a pivot here, and a free variable here. So I can say my third variable is t, my y is, that would end up on the other side, so 51 on 67 t, and my z is, my x is 65 on 67 t. And so my eigenvector is t lots of 65 on 67, 51 on 67, 1. Which does not currently add to 1. It's supposed to add to 1. So the quickest way for me to make it add to 1 would be to multiply everything by 67 first. Because I'm going to have to do that. Any multiple of an eigenvector is still an eigenvector. I've used this equivalent to as opposed to equal to. Because it's not exactly the same, because this t would be different to that t. And then I could, I guess, add them up and divide by whatever that number is, and then they're going to add up to 1. So 120, 170, 175, 6, 183. And so that's going to be ta-da! Now it's a probability vector. So there you go. And that there is called my steady state vector. So what that means is, whatever 65 and 183, that percentage of my ants are going to be in position number x. 35%. They're all roughly 30%. But the majority, the most ants are going to be in position z, and the least ants are going to be in position y. Which sort of makes sense. We have a lot of stuff from number 2 ending up in here. So there you go. I have a dream that one day I'm going to get 100 people and put them out on the maths lawns in little circles and get them to walk around until they make a steady state, because I think that'd be awesome. But one day. We've got to deal with the 25th anniversary of the Maths Learning Centre this year. Maybe next year we can do large-scale videos. Okay. That's pretty much everything I might say right now off the top of my head about Markov chains and dynamical systems. Any questions about anything that came up in that part of the course before I move on? Alright. I have to say that bit where I said that Markov chain is a special kind of dynamical system and that you can shortcut all the working because one of the eigenvalues turns out to be 1. That didn't make the slightest bit of sense to me in first year. To be fair, none of that made any sense to me in first year. Eigenvalues only started to make sense when I had to lecture them. But Yeah, I think that's really cool. That's really just the Markov chains are just a special kind, and you can skip half the working because you've got some extra information. Yeah. So my other list of, I'll go back to my emailed list and see what I've got, if my computer chooses to work. Now I'm going to get you guys to choose something. What would you like? Oh, yes?
To go through like regular partitions, to find the
All right. That was one of the things on the list and I was trying to avoid it, but I will do it. So just to check that I've got your question right, you're thinking about something along the lines of, and you're supposed to find like the integral of this from, I don't know, say 2 to 6.
if I like splitting that up into like n subintervals.
Yeah. Something like that?
Yeah.
Yeah. Something like that, where you've got an integral of something and you want to find this definite integral by dividing that into n subintervals and calculating upper and lower sums, that sort of thing. Right. All right. Okay. So this calculation is going to require me to do several steps, one after the other, and it's very useful when I do it, both for me and for the person reading it, or the person who has to read it, i.e. my marker. Both for me and the person who has to read it, it's very useful for me to tell the reader what the steps are that I am doing. So then I don't lose track as I go, and they can find all the bits they're looking for, and I can find all the bits I'm looking for. Okay. So the first thing you need to do is divide the interval that you're integrating over, in our case from 2 to 6, into n subintervals. You will do this even if you haven't been asked to do it. If you are asked to calculate, if you're asked to find this by using upper and lower sums, you will still divide that into n subintervals, because that's what the process requires, regardless of whether you're told to do that dividing into subintervals or not. And the dividing into subintervals takes some number of steps, which I can't calculate in my head at the moment. So, the first step is to figure out how wide each subinterval is. And I'm actually going to draw a picture of this. There's 2, and there's 6, and I've cut it into all these equal size subintervals, and there's n subintervals in total. And the width of each subinterval is called delta x. So that's what I'm going to calculate first. Right, so I have a big interval and I'm dividing into n pieces, and when you divide things into pieces and figure out how big each piece is, that's what division is for, and so I'm going to take the total width and divide it by n, and the total width in this case is 4. You probably have seen that formula as like b minus a over n, which is fine, but I have trouble remembering which letter goes where. It's easier for me to draw the picture and go, well, it's this total width divided by n. So that's the first step of dividing it into n subintervals. The next step is to calculate where the endpoints of each interval are. So I've figured out how wide they are. Now I want to go to the middle and find interval number I and tell the person reading it what the left-hand side of interval number I is and what the right-hand side of interval number I is. So this is number I somewhere in the middle. And I'm going to go do the right-hand side first. The right-hand end of sub-interval number I is normally called xi. That's normally what they call it. Okay, and I need to figure out how to calculate that. So the best way I know is to realise that I start at 2 and I add on I lots of delta x to get to the end of interval number I. So to get to the end of interval number 1, I'd start at 2 and add on 1 lot of delta x. To get the end of interval number 2, I'd start at 2 and add on 2 lots of delta x. To get to the end of interval number 3, I'd start at 2 and add on 3 lots of delta x. So it's starting at the left-hand side and adding on I lots of delta x. That's how you get to the right-hand end of subinterval number I. So don't be fooled by most of your examples starting at 0. It's not I delta x, it's the total left-hand end plus I delta x. And the left, well, let's just figure out what that is. That's 2 plus, and the delta x is 4 on n. Not particularly edifying to do that, but I've got it anyway. And the left-hand end of subinterval number I will be the step before that. So if the right-hand end adds on I lots of delta x, well, the left-hand end must be 1 lot of delta x before that. So it's I minus 1 lots of delta x. The beginning of interval number 1 is 2 and no lots of delta x. The beginning of interval number 2 is this and 1 lot of delta x. The beginning of interval number 3 is this and 2 lots of delta x. So it's always 1 less than the interval you're up to. So that is part 1. We've divided the big interval into n subintervals, and we've told the person reading it how wide each one of them is and what the left end and what the right end of each of them is. Starting with the right end because it's easier. Okay, the next part is to find where the maximum and minimum is on each interval. So, I should point out, this bit, it makes not the slightest difference what the actual function is to do this part here. You can do this even if this is fx and you don't know what it is. This bit requires me to know something about my function. I need to know whether my function is increasing or decreasing or neither. But when you're given one of these problems in Maths 1A, it's always either strictly increasing or strictly decreasing. Well, not strictly. It's either generally increasing or generally decreasing. It never turns up and then comes down again at the other end. But we're going to need to decide. So first I'm going to draw a picture of my graph on this zone. It's not to scale. So what's that? Y equals x squared plus 1. Well, x squared would be there, and x squared plus 1 would be a little bit higher. Okay, so my function is increasing. And therefore, being increasing, if I look at interval number I, somewhere in the middle, so function, I'm going to call the function f of x. It's worth noting that technically, sorry, there's my picture. It's worth noting that technically, if you haven't been told it's f of x, you're not allowed to call it f of x until you tell the reader what f of x stands for. That's how maths writing works. Most people reading your work in your exam won't care that much. There's not enough marks attached to that. But in an assignment, they might, or in a tube, they might do something to you. So, the function is increasing. It doesn't have to be increasing everywhere. I mean, technically the function is decreasing over here. It just has to be on the interval that you're actually doing the calculation. So it's increasing on the interval from 2 to 6. And why do I say that? I say that so the maximum occurs at the right-hand end, and the minimum occurs at the left-hand end. So you'll notice that the very first thing I did was to figure out where the maximum and minimum are. And then I will figure out what the maximum and minimum are. And I will choose whichever of them is at the right-hand end to calculate first. Okay? Always choose that because it's the simplest one to write down. So I'll choose the maximum because it's at the right-hand end. If I had a decreasing function, I would calculate the minimum first. So the minimum value, sorry, I was supposed to do the maximum, sorry about that. There's no reason you can't do them in any order, but this just makes my work easier. So the maximum value of my function on subinterval number I is f of the left-hand end. No, the right-hand end, that's where the maximum is. Didn't we just say that? Yeah, right-hand end. And the right-hand end was 2 plus 4i on n. And when I sub that into my formula, I get that, because it's x squared plus 1. So I'm just going to calculate what that is. That's 2 squared plus 2 times 4 on ni plus 1. So I've got 16 on n squared I squared plus 16 on ni plus 5. So I recommend calculating that to make it as simple as you possibly can before you do anything else, which is why I've done it here. All right. And the minimum value of f of x, oh crap, just a second. This is normally called capital MI up here, the maximum value. The minimum value of f of x on subinterval number I is normally called little mi. Damn it. Which is exactly the same thing, but with an I minus 1 instead. Which, if I felt like it, I could do the same by adding the putting an I minus 1 instead of an I into here if I felt like it. And there is absolutely no reason why you ought to expand that out. Leave it exactly as it is. Very important thing to point out at this point is that the minimum is not always the one with the I minus 1. Okay, it depends on whether it's increasing or decreasing. You need to look closely. The right-hand end goes with I, and the left-hand end goes with I minus 1. So if the maximum occurs at the right-hand end, it'll be the maximum that has the I, and the minimum that has the I minus 1. If the minimum occurs at the right-hand end, it'll be the minimum with the I, and the maximum with the I minus 1. The I or I minus 1 doesn't go with maximum or minimum, it goes with left and right. So that's step 2. Which, as you see, had 3 parts as well. So far we've had step 1, which had 3 parts. Step 1 was find the subintervals, and we've calculated the width of each interval and the left and right end. And then step 2 is to find the maximums and minimums on each subinterval. And first we had to decide where, and then we had to calculate the two of them. And then the next step is to find whichever of those has the I in it, as opposed to the I minus 1. So I don't know which one it is, but calculate whichever of those is from the right-hand end. So in our case, we're going to find the one with the maximum in it. Find the upper sum, since it has the I. Okay. So the upper sum is it's the sum from I equals 1 to n. Now that sum, those i's are referring to which subinterval we're up to so far. And on each subinterval you calculate the area of a rectangle. And the rectangle is delta x wide and capital MI high. In our case it's like this, right? You don't have to draw the picture, but delta x wide, capital MI high. And we're just going to sub in what we get from that. So just note this delta x doesn't change when I changes, so I can bring it out the front of the integral, sorry, the sum, because it doesn't involve an I. It doesn't matter which of these you can use either one as the definition, whichever one seems easiest to deal with at the time. Doesn't really matter. Okay. I might even leave it with the old one, whatever. Okay, so the delta x back on my first page was 4 on n. And the capital MI on the previous page was 16 on n squared I squared plus 16 on n I plus 5. And then I add them all up. So the way that the sum works is that the sum notation here is able to be expanded across addition the way that multiplication is. So that's one of the rules of how you can manipulate this algebra symbol. And anything that doesn't involve an I can come out the front of the sum. So I'm going to get this. That's just a 5. I have to leave something here. I could bring the 5 out the front and leave a 1 behind, but that's usually confusing to me when I'm trying to do it. So that's how I can do it. I can expand this out across multiplication and things, and addition, but I can't bring anything outside the sum if it involves an I. And now there's formulas for what these things are. The sum of from 1 to n of I squared has 3 pieces, and the pieces are 2, 3, and 6, and I believe it's n squared and n cubed and n. Yeah. So it's n squared that goes with the 2, and the n cubed goes with the 3, and the n, there's the last one. What's the sum of I? It's like a half of n times n plus 1, which is the same as, I'm just going to leave that there. And the sum of n lots of 5 would be n lots of 5. Beautiful. And now I'll expand this all out. Of course I will. So 16 divided by 2 would be 8, so I get an 8 there. 16 n on 3 there. Oh man. 16, I'm just going to write it like this. So those n's cancel, that becomes an 8, and I get 8n plus 8. Nice. Oh. So 8 plus 8 is 16. That's not too bad. 16 on 3 plus 8. Alright, so 8 would be 24 on 3. 24 plus 16 would be 40. Oh, there's a 5 as well. Aww. Oh, 45 on 3, which is 9. Nice. Love it. And I guess that would be beautiful. It could be wrong, of course, but you know. And so we have 64 on n there. No, that's an n squared then. Beautiful. So that's what I get for my upper sum. Nice. It will be a little easier to process this later if I put the plain number first. So already I can tell what the answer for the integral is. It's 36, and I really hope it is. Yep. No?
5 on 3 is 15.
Sorry? It is 15. Beautiful job. So that'll be 60 then, won't it? Which will change this to a 60. Oh, for fuck's sake, I've done that entirely wrong. $55. And so we're just stuffed, it's going to be awful. Yeah. So it's just bad. Right, there we go. Just like a good mathematician, I can do algebra, but arithmetic, you know. 220. Okay, sweet, we've got it now, I think I believe it. That's going to be the answer for the integral. Actually, I feel better that there's an on 3 in it, because if I integrate an x squared, I'm going to get an x cubed and then a third, and so it should be in thirds. Yeah, so I feel better about that now, actually. Okay, so we've found un. Now we have to find the other one. So, I'm not going to do that again. I'm going to use a fact about how un and ln are related to each other when it's an increasing function or a decreasing function. So let's have a look at this. ln is this. Right? And the little mi was f of 2 plus 4 on n x on one side. But the thing is that the un Oh, yeah. Was this. The only thing that makes them different is this minus 1 here. So if we think about what happens when we sub in the numbers from 1 to n, if I sub in the numbers from 1 to n here, I'll get the numbers from 1 to n. And if I sub in the numbers from 1 to n here, I'll get the numbers from 0 to n minus 1. So this is a little picture I draw myself, usually on the scribble paper. The ln has the numbers from 0 to n minus 1, and the un has the numbers from 1 to n. So if I do this one minus that one, all these ones in the middle are going to cancel each other out. And I'm just going to end up with those two. So un minus ln is going to be what I get when I use n times delta x. So this thing, when I use n, minus this thing when I use 0. Because all this bit cancels out in the middle. Beautiful. Which is 4 on n. Now, 6 squared plus 1. 2 squared plus 1. So what's that? 37 minus 5 is 32. 32 times 4 would be 128. So that's how far apart the un and the ln are. Which means that since I know what un is, I can figure out what ln is. So ln must be un minus 128 over n, which is whatever un was, 220 over 3 plus 64 over n plus 32 on n squared minus 128 over n. You will notice that the un and the ln almost always work out exactly the same except for a minus sign. So it's a good hint that I've done this right. Alright, so if all I was asked to do was to find the upper sum and the lower sum, I could stop now. But I was asked to find the integral. So I know that ln is less than or equal to the real value of the integral, which is less than or equal to the upper sum for all n. And for completeness' sake, I'm going to put this working in. So that's the un. And that's the ln, and this is the un. And the bigger n gets, the closer both of these get to 220 on 3, and therefore this is 220 on 3. called the squeeze law. This thing is squeezed between those two numbers, and those two numbers get closer to 220 on 3, and therefore it gets closer to 220 on 3 as well. So there you go. That's the deal. So I guess the final answer, I really should have put a box here, find the integral. That's the heading of this last bit. So let's just see where we've been. We divided into n subintervals, which calculated the width and the left and right ends and the right and left ends of each interval. Then we found where the maximum was, and where the maximum minimum are, and what the maximum and minimum are. And we chose the right-hand end one first because that's easier. And then we calculated the upper sum by doing all of our sum notation stuff. And then we calculated the lower sum from the upper sum using this trick here. And then we wrote some stuff and it said what the integral was. That's how that process goes. Note that in an exam, the lecturer is likely to do parts of it for you. Or ask you to say, for example, they might say, write an expression for the upper sum, in which case you'll just stop there. Write an expression for the upper sum that uses sigma notation, and you'd stop at that point, you wouldn't figure it out. Or even, it might be that you can't calculate this bit, you can't expand this bit out because it's sine or cos or something, and you just leave it with an f in it. So just be aware that anytime there's a complex procedure, in an exam they may only ask you part of it, and just take note carefully because you might not be able to do all of it, so just do the bit you've been asked to do. And if you know the procedure, the steps in the procedure well, then you can know which bits have been done for you and which bits haven't. How do you feel about that?
Oh, I got better.
Alright, cool. Alright, I've got about 15-20 minutes. What am I going to do next? Yep.
Is there a question about the formulas you used for I and I squared? Do I have to memorize them, or do I know how to write them through?
So you mean these things just here?
Yeah.
Excuse me. Unfortunately, not being your lecturer, I don't know if you're supposed to memorize them or not. I'm from the Maths Learning Centre, I don't run your course, I don't mark the exams, don't write the exams. I wish I could see the exams, but I only get to see them next semester when students come asking about them. I don't know. As far as I'm aware, you're definitely supposed to remember this one. And that one, but that's not a thing, that's just multiplication. I don't know if you're supposed to remember this one, but it's not the worst thing to remember.
Do I have to know how to write them?
No. Well, yeah, I don't know. The proof of how to get this from this is in the lectures. And anything that's in the lectures is a thing that you could be asked to do, technically. If you look at past exams, it's not traditional to ask you to do that. But, you never know. I'm sorry. Yeah. So if you do talk to your lecturer in their consulting times, which I believe are on Monday and Tuesday, no, Monday's public holiday, Tuesday and Wednesday, that's a good question to ask them. Questions about what you're expected to remember are great questions to ask the lecturer. If they go, I don't know, maybe you do, then remember it. Lecturers are really bad at pretending they don't know what's in the exam, so if you ask them the right sorts of questions, they'll give it away by the way that they talk. That's such bad advice, though. Yeah, if you're good at playing poker with lecturers...
You've got to watch out for the guy that double bluffs.
I know, the double bluffing is always the worst thing. Some lecturers just have it all down straight and they can do it completely straight face and say anything that's in the lecture notes could be in the exam. And they just practice it for years. Anyway, I have the advantage of actually not knowing what's in the exam because I haven't seen it, so that's easier for me. Okay, anything else? I am going to do another one next week. Let me have a look at so the other things people have asked me about by email are subspaces, basis and linear independence, and that's not going to happen in 10 minutes. It's not going to happen. I'd recommend going and having a look at the existing video on that. Optimization, reduction formulas, calculating errors associated with the Simpson's rule. All right, could probably fit Simpson's rule in. I don't know how you feel about that. Might as well fill it in since that will appease whoever sent me the email. I don't know what they're going to do to me if I don't do it, but okay, so on the website already, there is a bit of a seminar about how Simpson's rule and trapezoidal rule work. I hope, I mean, there is at least one. But the errors is a different story, and as far as I'm aware, you're not expected to remember the error formulas for the Simpson's rule and trapezoidal rule. If you need to use them, you're going to be given them, which is therefore why I don't remember them, and I'm going to need to look them up in somebody's lecture notes. If someone could let me borrow them. It's a race. Okay. So this is the part of the notes that goes with this. It's called Numerical Integration. So if you are looking on the website for this, it's under Numerical Integration. Right, here they are. Okay, so there are approximations to the real integral. The really weird thing about this is that almost always when you're actually using Simpson's rule, you don't know what the formula for the function is. All you have is a list of function values, and you don't even know what the formula is. So you could never in practice know this answer, because it involves differentiating your function. If you don't know what your function is, you can't differentiate it. However, this is of theoretical interest, because what it does tell me is that Simpson's rule is more accurate than the trapezoidal rule. Okay, that's the thing. Okay. So the best thing I can tell you is how to interpret them. So what we've got is we've got some sort of function. And we've divided it up into n subintervals, just like we do for upper and lower sums. But this time we have a specific number of subintervals. We're never going to do this as n goes to infinity. And those subintervals give you a specific set of heights, which you have a list of, somewhere in a table or an Excel sheet, or MATLAB or something. And those list of heights are called the yns. And so we have all these xn's, and the xn has like a yn to go with it. Okay. And both of the Simpson's rule and the trapezoidal rule philosophically are based on attempting to calculate the integral from the average value. So the theory says that the average value ought to be, is going to be the integral divided by the width for any interval at all, whether it's a big one or a small one. And so what I'm going to do is on every interval I'm going to average some of the values to figure out the average value and figure out the integral there. So I'm going to get the integral average value times the width. And then I'm going to add up all those little integrals to make the big integral. So for the trapezoidal rule, you average the beginning and the end of each interval. And so you have the left end plus the right end divided by 2. And for the Simpson's rule, you group these intervals into pairs and you do the average of the left and the right and 4 of the middle one on every interval, and you add them all up. So Simpson's rule trapezoidal rule. So it's f of the left plus f of the right divided by 2, that's the average value, times the width. And the Simpson's rule, you have to group them into pairs, so the widths are 2 lots of delta x. And you go f of the left and 4 of f of the middle and f of the right, which is 6 things, and so you divide them by 6 to get the average. And that's why you end up with a delta x on 3 when you do it, even though you've added up 6 things. Yeah. Anyway. And then you add them up. That's all I wanted to say. I just wanted to say I can't do Simpson's rule and trapezoidal rule without mentioning those things. And so what we can do is we can say that the error formula for trapezoidal rule, which is exactly how far apart your trapezoidal estimation and the real integral are, the absolute value of this error is less than or equal to k2 times b minus a cubed over 12 on n squared, where the b and the a are these numbers here. And it doesn't tell me what the k2 is. Right, there. K2 is a number so that the absolute value of the second derivative of your function is less than or equal to, damn it, is less than or equal to k2 on the interval AB. That's what that means. And the error formula for the Simpson's rule is less than or equal to k4 times b minus a to the 5 over 180 times n to the 4. Now, as far as I'm aware, you're not expected to remember both of these. So let me just say that's the fourth derivative. I've written in Roman numerals. It's traditional is to write it like that. You're not expected to remember the exact details of this. In particular, you're not expected to remember the number 180. All right? But it's important for you to have a vague idea that it's a fraction that has the width of the interval on the top and the number of the n on the bottom, and that it's related to, you need to know what the k2 and the k4 stand for, because usually they'll just give you this formula without telling you what the k2 is, and you have to remember that for yourself. Okay, so this is telling me that the second derivative is the curvature, so the more strongly curved something is, the bigger this formula is going to be, and so the more the error can possibly be when something's strongly curved. And this is the fourth derivative, which I have no idea what the word for that is. I don't know, crinkliness. So the crinklier it is, I don't know. The more strongly, crinkly is not right either. Kurtotic is the third one. I don't know. The bigger the fourth derivative is, the worse your error is going to be for your Simpson's rule. But fourth derivatives tend to be less extreme than second derivatives, and so you tend to get better, and you use an n to the 4 instead of an n squared, so you tend to get lower errors for the Simpson's rule than you do for the trapezoidal rule. Okay. which is totally an exam question that I would ask if I was writing it. I would say, explain why the Simpson's rule error, here are the formulas, explain why the Simpson's rule error is likely to be smaller than the trapezoidal rule error, and you say, well, this has an n to the 4 on the bottom, this has an n squared, so it's got a bigger denominator and therefore is smaller. Something like that. Okay. But what you really want to know is how to deal with this. So let's see how to deal with this. So what if we were going to use the trapezoidal rule to estimate well, that's 4 again. Sure, let's do that. Using, I don't know, pick a number, 3 intervals. How wide is this? 7. Yeah, it doesn't really matter. Okay. So from 3 to 10, oh man, that's sort of like from merely pi up to merely 3 pi. So we've got that, that's pi, 2 pi, so it's sort of about 10 is a little bit, is quite close to 3 pi actually. Okay. So the area is going to be, looks like, I mean, because the positive ones cancel out the negative ones, it's going to be this little bit. So it's probably going to be quite a lot less than 1. I know that one of these little bits is 1, so I'm guessing it's going to be about 0.1. That's my guess. It's got to be not too bad, but obviously trapezoidal will do a bit of job. Okay, but this is just an example, so we know how this goes. To calculate the error, we're going to need the second derivative. So let's see, k f of x is sine x, f dashed x is cos x, and the second derivative is negative sine x. And the absolute value of the second derivative is, well, the absolute value of sine x. I guess it's the absolute value of negative sine x, which is the same as the absolute value of sine x. And that function looks like this. When you absolute value something, all the negative bits become positive. And on the interval we're interested in, the maximum possible value for that is 1. And that's my K2. And that's pretty much the deal of how you do these things. You look at the graph and you make a decision about what the maximum possible value of that second derivative is. And sine is always less than 1, so that's nice and straightforward. And so therefore the error in the trapezoidal rule with 3 intervals is less than or equal to, now what was it, K2 b minus a, which was 10 minus 3, to the power of 3 over 12 times 3 squared, which is going to be an awful, awful number.
So b, that's 7 cubed is 349.
Yeah.
By itself.
Which is hilarious because we know what the answer is already. So good, we can calculate the area to within 2.24. We think it's 0.1. It's not the best error estimate, but whatevs. So we've got 3 intervals. Yeah, I have no idea what's going to happen. The bigger the number of intervals is, the better this is going to get. And the smaller the width of the zone you're out calculating, the better this is going to be. Okay. The only other thing you could be asked is, how many intervals do you need to get an error within a certain amount? No. Do you know what? Okay, that'd be a classic sort of thing that you might want to know, because one of the anytime there's a formula, it's common to be asked questions about what all questions that allow you to calculate every missing value in that formula, and so how many intervals to get an error within 0.0001, and so that would be, alright, we need the fourth derivative because it's Simpson's rule. Like that. And on this zone, y equals 24x, the maximum value is over here. So that's less than or equal to 24. Just be careful, remember that it's the absolute value. So I really should have put that other thing in there, an extra line. The absolute value of f. So that's technically that, right? So that's root 24. Just be careful with the absolute value is that don't just look at the strict maximum, because if it goes down really low below the x-axis, it'll be down there that the maximum value of the absolute value is. And so I'm going to get that the error in the Simpson's rule of n is less than or equal to k4 times b minus a to the 5 over 180 n to the 4. Yep. Which is and in order to guarantee that the error is less than 0.0001, I need to guarantee that this is less than 0.0001. So don't be fooled in putting the 0.0001 here. This isn't equal to that. We need it to be definitely less. We know it's less than this, and if we know that this is less than this, then we will be guaranteed to have it the way we want. So we'll rearrange this to figure out what n has to be. So, damn it, sorry guys. Oh, I could have left the 180 down there, couldn't I? And so n has to be greater than whatever the fourth root of that is. (24) divided by 180. To the power of a quarter. And so that's 6.04, and so therefore n has to be 7. Because it has to be properly greater than 6.04 in order for it to work. So I need to go up to the next one. And that's pretty much everything I could say about using errors for Simpson's and trapezoidal rule. Thank you very much, everybody. I haven't decided what I will talk about on Tuesday, but if you have any thoughts, feel free to email the Maths Learning Centre, and I will see you around. We are open all the way to the end of exams, just so you know. But not on Monday. No, it started with that before. Oh, damn it. Yeah. I didn't go far enough.
We know it.
It's still recording. Just a second. So back at this point, it's actually, that's the first derivative. This is only the second derivative. This is the third derivative. The fourth derivative is 24, right? And the absolute value of the fourth derivative is still 24. Which is less than or equal to 24. And the graph is actually just this. Yeah. Okay, cool. Fixed.
One more thing. The number of
Yes.
So this would be
Oh, you're right, my goodness. Oh. Simpson's rule has to have an even number of intervals. Yep. Oh, it totally is. I'm so not doing well today.
And then I'm headed to a thing.
Okay. Where are you going to do?
You see, after you've been
see you there,
speaking
okay.
for 2 hours, you seem to lose you. So when I put this up, it will be, just be aware there's some mistakes, and they're all corrected by the end. So for those who are listening, thanks for sticking with this to see what the corrections are.
Okay, sure. So when do you start the training? Thank you. Will we get an email about next week?
Yes, it will be at this time in the Darling West Lecture Theatre on Tuesday, but you will get an email.
Awesome, thank you. Shit.
Oh, someone left it.
Thank you.
It's not impossible. Email Maths Learning Centre so that it's in my email and then I'll find it. I should say that I did trig substitution semester 2 last year. Oh, well, I'm happy to do it if there's nothing else to talk about. I did... Actually, there is a decision-making process, actually, which I can tell you now. My decision-making process is based on trig identities. So feel free to look at it up there. So it's to do with the shape of the thing that you see there. So if somewhere in your integral you had a root, if you had that, for example, somewhere in your integral, then you'd be expecting to do a trig substitution because it's sort of a squared, plus or minus squared thing under a thing. And you can use trig identity / triangle to help you figure out what the right thing is. Okay, so the goal of trig substitution is to turn this into something that's a square, right? Yeah. So I can think about my trig identities that I know. I know this one. Yeah. And I need to see this has got variable squared plus variable squared equals number, and this has number minus variable squared. So it looks like maybe this is the go. Yeah?
Yep.
So what we need, so let's compare this to what we've got. I'm going to deal with the number first. This is a 3, and I've only got a 1, so if it just times everything by 3. Now the 3 matches. And now all of this has to be 2x squared. So what I need is 3 sine u squared would be 2x squared. So my x is equal to root 3 on root 2 sine u. And that's my substitution. And neatly, I've already done half of my work for me because I've also figured out what cos is. So what this means is now that 3 cos u squared is now 3 minus 2x squared because we can replace that with 2x squared. And so when I do the square root of both sides, right? Yep. Now this thing in the integral can be directly replaced with root 3 cos u.
Okay.
Which is the whole point of trig substitution.
How do you know if it's like a minus or not? Like
you arrange it so that it's a plus by doing this. Okay, so because technically this is saying that u is arc sine of x, of whatever root, whatever, and the domain of arc sine is this, which neatly happens to be the exact location where cos is positive, and the domain of arc cos is the exact location where sine is positive. So it's one of the reasons those were chosen as the domains. Not really, it's just a coincidence, and it's a happy coincidence, but it's nice, and that's one of the ways that I think about it. So yeah, and so that's you just choose a zone for u that covers all the possible values of sine, such that this will be positive after all. Yeah. So when you do it for sec, you actually choose those two corners, I believe. No. I think when you do u, I can't remember now. But yeah. Yeah, that covers all the values of sec, and tan's always positive in those corners. And so it's a separated domain, but it's just the way you do it. So that's the decision-making rule I take. And the reason I do it is because main reason is that I've already done half my working by the time I figured it out. Yeah.
Saves a bit of time.
Yeah.
Thank you.